All right, today we took the Reynolds transport theorem and converted it to a description of mass conservation for a moving fluid. The statement of mass conservation reduces due to the fact that the rate of change of the mass of a system of particles, where we're following those particles, is equal to 0. So the Reynolds transport theorem, the left-hand side becomes 0, and the right-hand side is simply that the rate of change of the mass of the control volume it has to be offset by the flow of fluid into and out of our control volume or through the control surface. And so we write this as the integral over the control surface of density times V dot the area element dA. Now, the way we can interpret this is that we have storage and net outflow. But we usually write this with the storage moved to the opposite side of the equation, and so we would have that the time rate of change of the mass in our control volume is equal to the negative of the integral over the control surface of the fluxes through the control surface. So this becomes the net outflow. Net inflow. So net inflow increases the mass in the control volume, net outflow decreases. Now this is the integral form of mass conservation. The discrete form, where we think about the flow through individual faces, would be written as minus the sum of over the faces, I equals 1 to n, of rho I vi dot ai, where we have velocity and area vectors. And the sign of that dot product creates negatives for inflows, which combined with this minus sign in front means that those inflows are positive. So we have change in storage is equal to inflows minus outflows. And this is the second form of the equation that we frequently use. And then the last modification that we made was to note that you can write vi dot ai as plus or minus qi, where q is the volumetric flow, where the plus or the minus accounts for the sign of that dot product, where in this convention outflows are positive. The last thing that we focused on was in a closed conduit, where you have flow along the axis of the control of the conduit, say from cross-section 1 to cross-section 2. Then we can say, using mass conservation, I won't go through all the details here, but V1 A1 equals V2 A2, or Q1 equals Q2. This is for a filled, closed conduit. And so I want to distinguish that result from the rest of these mass conservation statements, because it's an application of mass conservation that allows us to conclude that. And this shows that velocity goes up as cross-sectional area goes down in a way that conserves mass.